Don't worry, I'm just out. So, good afternoon to your audience. My name is Alexey Lukinchuk and I'm from Team Ukraine. And in the next 10 minutes you will hear my solution regarding problem number 17, balance in pebble. Our task was to investigate phenomenon when stones can be taken by wind, can be found staying on the same stand. And the main problem is to estimate its curve depending on the imported parameter. So, okay. To begin with, there are two factors that can affect the stand formation: sun rays and strong wind. But what is the most important one? We'll understand it during my presentation. So, my report will be structured in the following way. Please start from this slide. Yes, thank you. So, I'll start from observing of possible mechanism, then I'll estimate effect strange and simulate the lake formation. Having done it, I'll compare my results with the original photo, and in the end you will see our experimental step and analysis of obtained reproductions. So, to begin with, at the first look, it may seem that the process happens due to melting by sun rays, and it makes sense. There are shadowed regions and regions always exposed to the sun. Thus, the latter melt more intensely. But, after more precise analysis, we understand that lion's share of solar energy either reflects or propagates through the ice surface. But at the same time, a stone is heated. Thus, due to heat conduction, it melts an adjacent region. Consequently, it leads to stone sinking. And we can see that no stand appears. It means that sun cannot lead to this phenomenon. So, however, we know that wind may play the key role. Because we know that when wind flows around a stone, nearby region experience higher airspeed than outskirts, and it may lead to enhancements of mass loss. What is it? We'll see later. So, what is mass loss? For example, I mean it like weathering when small particles in wind due to turbulent pulsations or velocity can separate other particles from the surface, and sublimation and etc. So, to estimate this coefficient, I took the data from an article, and you can see a plot on a slide where it is depicted that this rate is up to 6 mm per day. Moreover, we can see that this rate strongly depends on wind speed. Indeed, when wind flows around a stone, the field of velocity is strongly non-uniform. It means that mass loss coefficient is strongly non-uniform too. So, and it may lead to stand formation. It leads to stand formation. Let's proceed to the theoretical study. This function, mass loss function, has as the most important parameters velocity and temperature. And hydrodynamics requires a function to be proportional to velocity. And since the process of debris separation is caused by activation mechanism, we expect the function to be proportional to the activation exponent. Hence, the following trend is expected. So we took also the data from this article, but if we just try to plot this dependence of coefficient of mass loss on temperature, we'll get a graph with big deviation. It means that, and we have already found why it happens, because we neglected air influence. And we can see that blue points that are associated with higher airspeed are higher than others. So, having normalized the data on velocity, we can get the plot with much less scatter, and normalized deviation has decreased in 5 times. And it means that our normalization is natural, and indeed we should take into account wind influence. So, these coefficients can be extracted from the fitting. So, the only thing that we need to conduct simulation are to find velocity and temperature field. A velocity field is described by Poisson equation with the following boundary conditions that are associated with irradiation and convection respectively. And we have solved this problem in Kamsel multiphysics, and as a result we obtain the following temperature field. And we can see that in the viscous layer temperature is almost constant. So we can safely neglect temperature dependence. So we conducted modeling using both C++ and Kamsel multiphysics. So how we do it? It's been done in several iterations. During each we took the share from previous step, put the data into Kamsel to calculate the velocity field. This field was calculated. This field gains the data to our own program region in C++ that calculated displacements of points on the surface, and thus we can obtain a new shape that should go to the first step and so on. So here you can see our obtained profile, and you can see the original photo, and it is remarkable that there is no change. It means that only dependence on velocity cannot describe the effect. So, but we know that turbulence may play a key role, because we know that trenches and snow around trees look similar to the surface around a stone, and it happens due to wind turbulence. So, why do you think so? Because when surface is flat, turbulence exists only in a very thin layer and it is linear there. And when encountering an obstacle, mass loss depends on turbulent kinetic energy as well. So we can get this formula. We calculated, we've conducted modeling one more time using the new dependence. So here you can see the velocity field obtained, and using this field we plot turbulent kinetic energy field, and you can see that at the closest region in the trench turbulence is significant, and it has proved that turbulence is really important. So here you can see the result of our modeling during few iterations, and you can see that we can see trenches and we can see a stand as they appear in the original photo. So to verify our theory, we took the original photo one more time, and here you can see at the top part the slides the results of our simulation, and at the bottom part the result of just getting the data about the shape using the original photo. So let's proceed to the experimental study. In our experimental setup consists of a fan and a pebble that were placed within a refrigerating chamber. So, at the following slides you will see a few of our obtained stands, and let me describe our experimental technique. First of all, to identify the shape, we took the modeling clay, make a cast of its surface, and then cut in half the modeling clay that we get. And here you can see the result that corresponds to the original shape. So that is our experimental technique. Here you can see few of our shapes, few of obtained shapes, and at the lowest part you can see just few of our obtained stands, and they look similar. And we can, but there are difference, and we can say that, for example, this difference can be described by additional influence of hardening. What is hardening? We know that there is phenomenon in geology when when it's stained on a soft pillar, it makes the pillar outside more strict and helps it to protect from weathering. So we can say that partially this difference can be described by this hardening. So we also know that there is influence of an angle between a fan and a shape, because when we move a fan there is a change in the turbulent field, in the field of velocity in general, so turbulence changes as well. So you can see the plot of maximal depth of a trench plotted on day, with corresponding to 3 different angles between a fan and surface. So let's proceed to conclusions. We found that the most important influence has the turbulent field, has turbulences, and we've proved it by conducted modeling. So we obtained few stands. We proposed a method how to get the information about shapes that we obtained, and we were able to say why there were some differences between them. And as a result we proved that theories that we've investigated why it explains the phenomenon, why it leads to the things that we can see. So that's all. Thanks for attention.
Can I start?
Okay,
Anytime?
sure, you're ready.
I actually have a name. I'm Max Blom, opposing Ukraine on balancing pebbles, in which the report was tasked to reproduce and explain a standing phenomenon where pebbles, after a storm, stand on a thin stand, and then estimate and explain the curve parameters, and also explain the important, like this, parameters of this curve. Our interpretation is to reproduce this phenomenon, and then try to qualitatively and quantitatively explain the phenomenon, and then also, as the problem description read, find a curve dependence based on these parameters. If we start with a theory, what the reporter did well was to explain what we can exclude, and provided an extensive list of this. Also considered wind to be an important parameter, and extracted data from articles to support the claims made. However, the explanation was a bit rushed, and we didn't fully get the hang of how all these parameters were fit together. In the beginning, it tried to fit a curve without any prior explanation. When we fitted a curve, it said this doesn't really work, and that we have to take into account a deviation from it, but didn't really go into how this mechanism behind this works and why you exactly chose this. This is both theory and experimental, went into a simulation, which in what we experienced only took account for the temperature and mass flow, but did not take into account, for instance, the stone weight, stone temperature, or what were the initial conditions, for instance, in this simulation. Also assume no condensation on the stone or other physical interactions between the stone and the surrounding world. The experiments and simulation. What the reporter did well was to provide numerical experiments and compare these with verified results. Also made a very good analogy to geological erosion, in which the same phenomenon is occurring. However, again, the simulation excluded the possible important parameters such as stone temperature, distribution, and how these parameters were varied over time. Was this constant during the experiment? Was the stone preheated or something during this process? Because as we know in the real world, the parameters change over time, and it's not that it has been a steady state and suddenly it blows and we have these formations. Also used a fan to make a wind. Now there's a very important distinction between a fan and a storm. First off, a fan has highly non-laminar flow and is very turbulent, and we didn't really receive any specifications. However, in a storm, first off, we have more laminar flow, and most importantly, also, and the strength. There was no mention whether or not the strength of the wind had any specific dependence, or if it's equivalent. If a strong fan would have the same effect as having a weak fan, but turned on, having this process over a longer time. And again, provided no quantitative results for the curve, the problem descriptions said to find the curve dependence and the curve shape. None of this was mentioned during the entire presentation. And I'd like to move on to the discussion, in which I'd like to ask the porter how the ambient temperature variations might contribute to this. If we consider Lake Baikal over this season, there are of course temperature variations. The stone might get heated before a storm, the various winds and turbulence, the humidity in the air.
Okay.
How did you take into account for these?
Let me use my presentation, please.
Yes.
If you don't mind.
During the dangerous position.
5 minutes of discussion.
Vika, could you please open an additional slide? Additional slides. Okay, we can just discuss something that you've been told about. For example, you told about press this button right. No. Press the first slide and press the button, orange button at the top. With okay, and where is it? Oh. Okay. The next slide, please. The next. Oh, previous one. That is the role of humidity. The next one. I've tried to conduct this similar normalization using the data about humidity, because I've took the data from an article, and there are very lot of data in this article. There were data about humidity, there were data about solar flux, etc. And I've tried to do the same normalization as I did to velocity field, and we can see that there is no result. You can see that there are blue points that higher than the curve and that upper than the curve. And we see that humidity doesn't have a so important result as velocity have.
How were these experiments, these results taken? Because from the source, how did the source conduct these measurements?
Okay, it was a geological article. They had a specific station. They collected data about humidity, about about other things, and I've just used this data. Sorry, probably I didn't get your question.
Okay. All right. I think it's better to move on. If we could switch to the.
We can discuss about no curve. It's an interesting question because I think that my theory is my modeling. Because in modeling I used the theory that I'd introduced. So, as a result of my theory, I've shown you few of our shapes, and the shapes that I've shown, that is the result of my theory.
I know, the model, I'm not saying that it's bad, however, when you're presenting it, there are a lot of things that leaves us wondering, what if we change this, what if we change this?
For example, temperature, yeah?
Well, what would happen if we would take a very cold stone or a hotter stone, for instance, these...
But we know that characteristic time for this process is really long. It decades of dates, it doesn't have sense. It's like 10-20 days for this process. And we know that temperature can change significantly. Because when we place a stone on ice, the temperature of a stone and ice, they are similar. Why do we expect that they are not similar?
Well, depending on the day and night cycle, you will have various temperature variations, also various wind variations.
Yes, but wind is much more important.
And the data to support that is...
I've shown you the result of my modeling for temperature field, and we can see that in the closest region to this ice surface, the temperature is almost constant.
All right. Also, a question about this: is this data specifically for this kind of phenomenon, or is it just general for ice and?
Yes, but when time is more than I don't know.
Yes. However, is this the data you've obtained? Is it specifically for this phenomenon, or is it just general data about?
General data about mass losses.
All right. So how can you conclude directly that this is?
Okay, it's interesting question. Thank you for asking. Because in my theory, I think that this process happens everywhere, and the most important factor is velocity, turbulent energy. And if we have a plate surface, this phenomena also exists, but turbulence exists only in a thin layer. And when we have a strange shape, we have another turbulences, and the only dependence is on.
You can continue later.
Okay.
Now there are 2 minutes of discussion. 2 minutes of question from the reviewer. Okay, 3 minutes from now.
Hey, I'm Johan from the Faultiere, and I want to take a little review of the problem. Here's a task, some shorter. We see we want to find the circumstances why we find this special shape, and also try to reproduce it, and give some explanations also with simulations. So let's take a look on the reporter side. I really liked your style of presentation. It was quite clear and short and well structured. You describe a lot of different theory models and go into this sun topic and the wind topic in a quite deep direction. And also mention some further theory like turbulences and this higher stone structure. What I missed a little bit was the explanation of the theory, how you did it in reality. So how you set up which parameter you put inside and what you get exactly out. And especially the experimental side, that in my opinion, your model is quite limited because you has not taken into account the wind temperature or some stone parameter like also the temperature or size.
1 minute.
And the opponent? I really liked that you mentioned a lot of limitations of the model, especially in the experimental setup. I really would like also to see the experimental setup, what you did or what you built there. And so you have a lot of interesting theory points. And the opponent mentioned also some parameter I think you have to consider. For example, stone weight, wind speed, temperature, and so on. And this leads to some interesting points of discussion. For our team, for example, it was also the question, how are the circumstances there at the Baikal Lake? So what exactly happens there? Can you have some seasons changing on the ice? What is the temperature there? Is there ice over the year? Then can you describe if you use some different sizes and colors?
You may continue discussion.
Oh, yeah.
Okay, I think we'll start from the first one, from the first point. About wind direction. Actually, we know that Baikal is a great lake and it is quite flat. So we know that yes, there is dependence on wind direction, because if we see also almost isotropic stand, it means that wind have been isotropic. So, but if we see not isotropic, it means that there were one main direction. So, why do you mean? Sorry. Temperature. I said that I proved that temperature is not so important. I had the data about temperature, and do you know I have a data about fitting with exponent. And if temperature were important, I actually can add it to my model, to my modeling.
For example, I mean, do you have some experimental tests with, for example,
data about temperature on
radiation from the heat radiation or matter of the melting point or so? So did you try to to measure in some kind experimentally the temperature?
So temperature, as I said to your team member, temperature was -5 degrees. Sorry, probably I didn't get your question. And I think that the most important factor is the shape of a stone, because the main parameter is turbulences, and turbulence are caused by the shape. So the shape is the most important factor that can affect this information.
Okay, one question to the opponent. I have here another interesting point, I think. So do you think that adhesion can also be a cause of this kind of round shape under the stone? You know, if it's melting a little bit, then the water's coming upwards?
I'd say that specifically at one time point, I wouldn't say that this is the driving factor. I'd say that since this is a phenomenon that occurs during a long period of time, it would be worth measuring and finding out if the variation in temperature, also sunlight, and also wind during this longer period of time would cause, during this period of time there is a time for both melting a bit, the stone heating up and melting, a condensation on the stone, which could then further build up this layer of ice. And as I mentioned, due to these variations, it is very likely that these processes are occurring during, as you mentioned, over a period of time of, say, 10 to 20 days for this phenomenon to occur. Then I'd say this is very likely.
Okay, let me answer a few of these questions when my team member will switch to my presentation. So I'm going to tell you about the dependence on the color. So as I said, color is defined by coefficient of albedo, the coefficient of refracted light. So, and as I said, temperature is not so important as the velocity field. So velocity field is much more important. And I want to show you the data from this article I've told you before, and you can see.
But did you make some tests also with some
at Baikal? I've never been there.
Darker.
Okay, so I will tell you about
discussion.
We can also discuss.
Oh yes, can join the discussion.
Yeah. So it's open discussion now. First questions. For example,
I'd actually like to ask a question about the color. You said you did this an indoor experiment. Was it outdoor experiment you conducted?
My own experiment was done within a refrigeration chamber.
All right. When you said you varied the color, it doesn't really do much since fluorescent lights are only emitting depending on three principal frequencies. It's very different from having a sun.
I've proved that sun has no influence on the effect.
Well, you had data that it had no effect on just generic conditions of ice, not specifically on how it affects the stone.
So also you can see, I'll show you the information about this article, and they also measured a solar flux, and I have also tried to conduct a normalization on solar flux, and
yes.
I'll show.
One small question.
Yes, I have a very question of how does the shape of this curve, which was actually the question of investigating, how does that depend on, for example, the wind speed or the shape of the stone?
Let me discuss it one more time. I'm saying that my theory is my modeling. So no, in another way, the result of my theory is my modeling. Turbulence is a really hard theory. We cannot just write a formula and say that for this wind we will get this shape. It doesn't work. We just have to write theories and conduct a lot of calculations for. And we cannot just write a numerical formula. There is no analytic formula that will
but
be
I
an
mean the
answer.
comparison between your curves that you obtained.
Sorry, what do you mean?
So I would give maybe the chance to another question here.
Yes, so can you determine any threshold parameters, like maybe if the wind is too hard that the system can't be stable, maybe the stone will be fallen down before really the couple can evolve?
I can make a calculations right now estimation if you want.
Did you do?
Okay,
No.
let's do it.
No, can you show us, did you do it?
I'm
already?
sorry. Okay, I can do it.
No, did you do it already?
No, I've never done, but I can do it right now. I think
Okay, so
it's
you
not
don't,
so
you don't
hard.
have yet some threshold parameters where you can say
I've not,
only
but-
under those conditions you can
I've not.
show this.
When we're talking about this, maybe it's also an interesting question. On the one picture you find a shape like this, you know, there's some smaller step, another kind of plate on your picture.
And I can explain it if you want.
Yeah, that
Because
would be interesting.
I'll take this one. So, because we know that everything happens due to wind, as I've said, and when wind flows, there we can see such turbulences. And at this region, turbulences become much stronger than at these points, because here we can, there is a pebble. So at this point, turbulences are not so high at this point. So this region becomes down and
Okay, so yeah.
Well, just to clarify, does your model say anything about the shape of the curve? Can you use your model to predict
yes,
the shape?
if you give me a shape, I'll put it in my program and it will give you a form, a shape.
Can you say anything qualitatively about this?
Qualitatively?
Yeah, is it
So-
proportional to the
Okay,
wind speed
okay, let me-
linearly or is it?
It depends linear on turbulent energy.
Okay.
And you know, I cannot just say about turbulence in a specific region, because you can see here the streamlines. I don't know whether you can see it clearly, but they're really strange, and we cannot just say by looking on them. We cannot write precise theory for the turbulences. All the theories for turbulences, they are not precise. They were done with a few fitting parameters. So it is really hard to analyze the turbulences, and we can do it only
Okay, yeah.
numerically, as I've done.
Come back maybe to this question. Do you think that the ice level is deeper than the tip?
Deeper.
Or-
Yes, stone is high indeed, and you can see it.
Yeah. Here, question.
Very
I
fast.
have some point to add about the parameter variation, because indeed in our report we variated on the slide number 39. We showed you the variation of the angle
Fast,
of
fast,
the
fast,
wind. It was discussed in the polemics, and this is the dependence of the maximal depth of the stand on the angle of the wind. So this is our experimental result, and the fitting to find the coefficient. Yes. And what about the color of the stones? I would like to say that
Just one sentence because the time is.
if we can reproduce the phenomenon in the refrigerator camera without the sun, it shows us that the sun is not the crucial factor for the stand formation. Thank you.
Thank you. Other reporter, you have 1 minute for concluding remarks.
Okay, I want to say one more time about the theory, because I think that modeling is a theory. And so indeed there are important factors, and the most important factor, as I said, is turbulences. And we cannot just write a formula for them, but if we have a shape of a stone, you can put it into my program that works. My program worked, and it gave us as a result that we can compare with the experiment, and we will get agreement. So I want to say that basically we obtained a program that worked, that can get us the results that you said, and probably that's all that I want to say. And thanks you for beautiful discussion. It was really great.
Okay. You said that the function h, the derivative, is proportional to u. Why?
To velocity? You mean this?
Yes.
Okay. Please open additional slides one more time. Okay, I'll try to explain it, because we know that this happens in an adjacent region, and we expect that thickness of an adjacent region is proportional to velocity. So, okay, I already explained it, so I already explained, so you don't need to do it. If I answered your question.
Yeah?
Okay, thank you. So we only observe it at Baikal Lake. You don't see this phenomenon in your regular winter, right? So what is so special about Baikal Lake? Probably there is some threshold on the wind speed.
I'm not sure because I achieved
Did
it.
you check this experimentally that if the wind is slower than something, no effect? Did you check
No.
this?
No, I think that we can. So my
The only threshold of the airflow velocity is actually for the turbulence to take place. If there is no turbulent flow, then there is no.
I see.
It explains that only with the laminar flow we cannot get the stand. We will get.
So you said that the sun is not important, but
It is not so important.
Okay.
The most important is the velocity.
And I can add additionally that this effect can actually be observed in the caves when there is no direct sunlight acting on the stone, so it's actually kind of verifies that the effect of the sun is not that important on the shape and to observe this effect.
okay, it wouldn't happen without wind. This is the statement, right?
Yes, the wind is the most important one.
But maybe the subleading effect is the thermal conductivity of the stone and the color on the top. Okay.
Maybe, but it's not so important.
And if the stand becomes very thin and the temperature is close to the melting point, then maybe also the increased pressure. Did you?
No, as I've said about hardening.
No. If you increase the pressure, then the temperature, then the ice might start melting away.
Yes, indeed.
But probably this is not the case in the real conditions.
No.
Can you show me again the slide that you talk about the Poisson equation, please?
A few seconds, please. This one, I think.
Oh yeah, and can you explain again why you use this and why? What are the boundary conditions?
You're talking about zero in the right side or about boundary conditions? Boundary conditions.
Boundary conditions.
Okay, we included two different mechanisms. We included irradiation, that sun emits some lights, and here is this term. And this term is proportional to the convention. So I put two different mechanisms. I included them, and I don't know whether I answered your question.
It's fine.
Okay.
What are the effects of evaporation?
Evaporation?
Yes.
I think it's not so important because temperatures are really below the zero, like -10 the Baikal, and they are not so important as weathering. Because I achieved the shape within refrigeration chamber, and I don't think that we have evaporation there. And also we expect that evaporation should be proportional like probably to humidity, something like that.
So are you saying that the phenomenon is only weathering, it's not sublimation?
No. Sorry, probably I skipped it very fast, but I said that mass loss, and it is weathering plus sublimation plus other not so important things.
The question is sublimation important? I mean, you said evaporation.
Evaporation.
I don't know if is that what you meant when you answered this question?
But the question was evaporation.
Well, there's
yeah, but there's no liquid water. So then technically it's not evaporation, right? So did you mean sublimation?
No, I mean evaporation.
Okay.
Evaporation is not so important.
Yeah, compared to sublimation.
Yes,
That's what we.
Okay. Thank you very much. Now the jury